What if I tell you there is a hidden source of error that actually fucks up your complex parts more than the calibration of your machine or your slicer settings? Hi, Andy here. What is the most accurate you ever got one of those calibration cubes to? For me, that's about 0.01 millimeter. But why is it then that every time I try to print something more complex, it all of a sudden doesn't fit anymore? Most people see a slicer as a translational step, but it actually can change something. To look at that, I actually co-authored and published a peer-reviewed scientific paper. So let's talk about what we found out. So as you guys might know, I work in medical 3D printing, and if it's something medical, it has to be accurate to our source data. So we window those data from, for example, CT scans, and then we have the conversion step into STL. This can already introduce slight errors. And at the end, we print it. Again, we introduce slight errors. So we want to make sure that everything in between is as accurate as it can be. But when we looked into it, we found out it actually isn't. And the result is more shocking than I thought, because this actually changes the way that I print every day and that you should print at home, even in normal mechanical applications. So let's roll it back a little bit. Everyone knows these calibration cubes. We have hundreds and hundreds of videos on YouTube how to mechanically calibrate your machine to perfection. And there is another 1,000 videos just about slicer settings and compensations and anti-aliasing in your slicer settings. But there's always one step that people completely overlook, and that is slicing itself. It's not because nobody wants to look at it, it's because it's hard to quantify. So what we did is actually try to find out if a slicing engine introduces an error into your part before you even press print, before all your thermal retraction, your extrusion errors and stuff like that compound and change your part. So when I started 3D printing I think it's now about 16 years ago, these calibration cubes were like my nightmare and my dream at the same point. Because I wanted my machine to have the most accuracy I can get out of it. And I always thought when I just measured the movement of my nozzle, I'm in sub-millimeter range, like way below millimeters, hundreds of millimeters. But when I printed those cubes, I ended up on like 20.00. And I even took measurements with like more accurate measurement tools. And I still ended up on the dot on zero. And I calibrated everything from X, Y, and Z to curves, to holes, to everything. Everything seemed perfect. But then I sliced the more complex part, and all of a sudden it wouldn't fit to its counterpart anymore. And I was furious. I thought it's about resolution of my STL, or about the speed I extrude with, or my material just being cheap and shit. I never found out what it was. You normally just introduce a little bit of tolerance into your part and call it a day. But if you want to have accuracy and you need accuracy, that's another topic. So what we actually did in this research paper is we took a lot of different slicing softwares and we kind of compared them to each other, but more importantly, we compared them to the original model we created. So our goal was not to have the most accuracy to real life part, like a 3D scan or a CT. We just wanted to see how the part behaves compared to its STL file. So you think, oh, easy. You just get a file, you slice it, print it out, and you take a high accuracy 3D scanner to it, and you just do a comparison. Thousands of studies did that, right? But here's the problem. With this methodology, you basically compound all the errors of your real world onto your part. So if your extrusion is a little bit inconsistent, if your machine is like in a very heated environment or something retracts uncontrollably, you measure that accuracy with it. So what you actually did, you compared STL to real life. We want to compare STL to slice part. So let me explain how we get around that problem. So what we actually needed to do is to have our G-code file converted back into a part. So a G-code file, as you know, is just a list of instructions for the machine. It tells the machine where to drive, how much material to put out, and how to compensate, for example, in curves for the edginess of the STL file. So we did that by employing something called the marching cube algorithm. Funnily enough, this marching cube algorithm was actually invented in the 1970s to reconstruct anatomical data from CT imaging. So it is very well studied, it is very accuracy. The thing you need to know it is very low in computational load. We want to quantify how much error actually comes from my slicing engine and how much error actually comes from my mechanical system or my material properties. So we chose a data set of 20 different mandibles and we chose 5 different well-known slicers. Those slicers, at least back then, were the main ones. And if you're wondering why I didn't do bamboo slicer actually is based on Prusa slicer. So I think having Prusa slicer as a baseline comparison is good. In medicine, you oftentimes use Simplify 3D, for example, because it's a well-studied industrial slicing method, even though in hobby markets you will not find that slicer anymore. So the methods that we use, we slice them in 5 different slicer engines with exactly the same settings. Nothing changed in between them. And there will be no physical printing involved. And we want to compare the generated G-code directly back to the STL file. So we are comparing without any physical intervention in between. We just want to see what the program itself does, because let's be honest, it's kind of a black box how a slicer gets to the G-code commands. And that's exactly what we wanted to look at. Of course, slicing 20 different mandibles in the same position with the same settings isn't something hard to do. So that was done pretty fast. The actual culprit or the actual problem we had is to reconstruct this accurately without introducing any errors into the reconstruction itself. There are websites out there where you can just upload your G-code and you can download your STL file. We didn't want to use one of those because we can't tell if those are accurate. Like, how are they reconstructing? Are they basically extruding it in a virtual world and then shrink wrapping it? Are they using algorithms to follow the extrusion lines? What do they do with extrusion multipliers, for example? So all of this was unknown. So what we decided to do is to use our own reconstruction method and to write all the needed code for it ourselves, so we know exactly what is happening. So how did we do that? First of all, after slicing, we just imported our G-code file basically as a text. So as you know, a G-code file is just an instruction for your nozzle to go from here to here and turn the motor that extrudes your part or that extrudes your material so much. It's not more. It's not complicated. It's not rocket science. It's just G-code. So with that, we can already graphically basically recreate our part. But there is a problem. A G-code doesn't have the information about volume in it. It just tells you to drive 0.2 millimeter higher and drive over there. So you have an infinitely thin line, but we need a volume. So what we did is so-called voxelizing. You can see voxel as one of those calibration cubes. A voxel is basically the 3D representation of a pixel. So basically a pixel is just a little surface on your screen, and a voxel is the same thing but in 3D. So with this voxel, very, very tiny voxels, we actually reconstructed everything that was in here. So we just clouded the mandible with voxels, and then the voxel just has one of 2 states: inside the geometry or outside of the geometry. If it's inside of the geometry, it has one value. If it's outside, it has the other value. Then we basically use something called a marching cube algorithm. So what this does is actually basically what it says. It's a cube that virtually marches along a given path. So this cube, of course, has 6 sides and it has 8 corners. So what it basically is a representation of a 256-bit data set, because there is 256 combinations of this corner that could happen if a cube marches through my model. Like this point is inside, this point is outside, outside, inside, outside, and the combinations are 256. So the good thing about marching cube algorithms is it's already computationally solved. So we don't need to put in a lot of computational effort to basically figure out what this combination of point activities mean in terms of the surface itself. We can simply look it up in a lookup table. So what this cube does, it marches around the surface And whenever it goes inside of my on voxels or my inside voxel, the corners are activated. If it finds 3 corners that are activated, it's basically made into a triangle. And all of those triangles, like I said, are already solved. So what we get is basically a remeshed version of our voxelized G-code in a super high accuracy. We are talking about millions and millions of triangles. We can be way higher with our triangles than our original STL because we don't have to render it, and it's basically just a table that you look up states. After we did that, we actually meshed it back into a standard STL, and from there on, it's simply comparing parts to each other. So we took the STL that we recreated digitally to the STL that we made that we exported or that we sliced from, and we compared them to each other. And the results were, let's say, surprising is an understatement. You see, when I print something, my normal accuracy, and probably yours as well with modern machines, is about 0.1 to 0.15 millimeters at a maximum. So whenever I measure something like a cube, a very easy surface, my accuracy is actually within like nothing. I can't even measure it with my normal calipers, or it's like 0.01 below. But as soon as I have a curved surface, nothing fits anymore. But let's get back to the big question that we're here for. How much inaccuracy is actually introduced by a slicing? And for all the Prusa fans out there, nice for you. The Prusa slicer was the most accurate, but it still introduced about 0.07 millimeter of inaccuracy into this standard mandible. But there are slicers that are way worse. For example, the most industrial solution, Fusion 360, introduced well above 0.1 millimeter of inaccuracy in your part. So now you think like, okay, it's like 0.07, 0.1 millimeter. I don't care. I always do 0.2 millimeter of clearance between my parts and everything should go fine. Locally, we sometimes have an accuracy on this part of more than 0.5 millimeter, just in your data file. Like, think about that. Before you even hit print, you're already 0.5 millimeter off. So that tells me, make sure you have the right slicer for the right part, because that matters. And that also tells me that all those manufacturers should look into their slicers and figure out what's going wrong there. So you think like, that's all nice, but like, what does that mean for my actual physical part? So what I did, I actually printed one of the mandibles we used in our study, and I partnered up with Revopoint. They sent us over their newest 3D scanner, which is a high accuracy blue light scanner. And what we will do now is we will actually scan in this part together, and then we will compare the actual error on the part to the error and see how much percentage that actually makes from our part. So let's go. I printed out one of the mandibles we used in our study. They are, by the way, from a public data set of CT images. And what I want to do now is I printed them with the exact same slicer setting that we used in the paper. And now I want to 3D scan it. Of course, as I told earlier, you compound all the errors of the slicer and the printer, but because we now know the errors of the slicer, I can basically subtract them from any error I have here. Why am I using a blue light scanner? So this one is the MetroX from Revopoint. The thing about blue light is blue light has a shorter wavelength, so it gives you, when it is catched by cameras, more accurate representation. So the accuracy of a blue light scanner compared to a white light scanner is a factor of magnitude, basically. So that's why I'm using a high precision 3D scanner instead of the more cheaper 3D scanner you saw in my earlier videos. We want to have it as accurate as possible because we don't want to stack the accuracy or the errors of the scanner itself on top of our analysis. I would say let's start the scan, see how it comes out. I see you in a few minutes. the results are in, and I think it's kind of shocking and funny because when we did the study, we didn't compare physical parts. It was not in the scope of the study. We wanted to see the inaccuracy that your part made. I printed those with my normal standard everyday printer that is very well calibrated because like I print a lot of mechanical parts that need to fit. I will show you the video of the comparison. We used an industrial certified software to compare our 3D scanned and our STL part to each other. And what we find out, if we go to unsigned, of course, the error is very minimal. It's actually within the margin that we found out that your slicer introduces into the 3D printed part. So basically my machine was perfectly accurate. If we go into signed, we can actually see that our error is about 0.6 millimeters. That's exactly what our paper found out the 3D slicer introduced in our part. So I think when you 3D print at home, with the current accuracy of our mechanical gantries that we have, with all the calibrations you do, all the dialing in and the slicer settings you do, more of your inaccuracy of your part is dependent on the slicer engine just messing your part up than it is on physical material retraction or physical error introduced by the machine. And I think that's something very interesting to find out. So it's not you, it's not your skill, it's actually the slicer. Do whatever you want with that information. I don't know how we should solve that. Maybe you have an idea, leave it down in the comments. And by the way, you can also read the full paper for free down in the comments as well. So thank you for watching, see you next time.